Welcome friends. This is the third lecture of impact of jet. Now let us revise once again the impulse momentum principle. You know, the impulse momentum principle says that rate of change of momentum is equal to the resultant force in the direction of flow, or change in momentum flux is equal to the resultant force. You know the flux is anything per unit time. So we can write that equation as F is equal to mass upon time to change in velocity. That is, mass into velocity is the momentum. Initial and final momentum rate will give you the force, resultant force. Now mass upon time can be written as mass upon volume into volume upon time, where the mass upon volume is mass density rho, and we know that discharge is volume upon time, and which can be written as area into velocity. Therefore, finally, we can write the equation for resultant force as mass density rho into AV into initial velocity minus final velocity. So, this is the basic equation we are going to use for finding out the force in different cases. Now already we have seen for the flat plate, which is fixed plate, the jet striking at the center at 90 degrees. The force, resultant force equation comes out to be F is equal to rho A V square. That already we know. Now suppose second case we can take that the plate is fixed but it is slightly inclined, and to that fixed inclined plate, if jet strikes at the center, what happens? How the force is calculated? Let us see. I'll go to the first slide of it. So you can see here I have shown a fixed plate, that the hatched inclined fixed plate which has angle theta with respect to horizontal. Can you see? Yes. Where v is the jet velocity, let us see that jet velocity we take as x direction. Now if suppose I want to find the force normal to the plate, that is Fn, you can see Fn is at 90 degrees to the plate. Okay. If I want the force in the direction normal to the plate, that is in the direction 90 degrees to the plate, then we have to consider the velocities at inlet, that is at point number 1, and outlet, that is at point number 2, should be in which direction? Obviously the direction of Fn. Therefore we have to calculate the components of velocities at point 1 and point 2 in normal direction Fn. So you can see here at the bottom I have shown the velocity diagrams. At point number 1, how the velocity of the jet, yes, it is in x direction. Now the angle theta you can see here is shown where the normal component of velocity at point number 1 comes out to be v sine theta. Okay, this is point number 1. Now you go to the point number 2, you come left bottom part. I have shown there. Now the velocity of jet when it leaves the plate at point number 2 is in inclined direction. Therefore its component in the normal direction, that is in the direction of Fn, should be equal to 0. Therefore now while considering the initial velocity and final velocity in the equation of resultant force, we have to take into consideration these two velocity components. Let us see how it is incorporated in the equation. You can see the same plate I have shown there. Now coming to the basic equation, Fn is equal to rho a v, that is the mass upon time, multiplied by initial velocity minus final velocity. V1 minus V2. Now V1, V2 already we have calculated. Therefore, Fn becomes rho into A into V multiplied by V sin theta minus 0. Therefore, Fn comes out to be V rho A V square sin theta. Now, if we want to find out its components of the force, then we can find out by considering the angle. Therefore, Fx becomes rho A V square sin theta, that is Fm, multiplied by sin theta. Fy, Fn multiplied by cos theta. Therefore, these expressions of Fx, Fy also can be calculated like this. Now, we can go for the next case. See, I have taken the curved plate now. Okay, so slightly modification we have done from the flat, then the incline. Now this plate is curved plate. Still it is fixed. The plate is not moving. At the point number 1, jet strikes in x direction. But when the jet leaves the plate, it leaves at the angle theta in backward direction. You can see in the diagram. Now equation is same. Fx is equal to mass flux, that is mass upon time into initial minus final velocity. So you can see the first bracket of Fx is rho av, which is same in all the cases. But when we consider the initial velocity and final velocity at point number 1 and point number 2, we can see clearly at point number 1 what is the jet velocity in x direction. It is v itself. And at point number 2, the jet velocity is now in the backward direction, that is v cos theta. Okay, so v cos theta I have not shown there, but v cos theta is the final velocity in the direction of x, rather opposite to the direction of x. That's why in the bracket, second bracket, you can see that v is the initial velocity minus of minus v cos theta. Now that third inside bracket I have given minus sign. Why? Because the component is in negative x direction. So finally the equation we get as Fx is equal to rho a v square 1 plus cos theta. So here we have to remember that mass flux, that is mass upon time, this expression remains same, rho a v. But what changes? The second bracket, initial velocity, final velocity. Similarly, now if we take the case number 4, same curved plate which is fixed, but now the jet is not striking at the center, but it strikes at one of the tips. You can see the second sketch at point number 1, that is we can call as a inlet point. The jet strikes the plate tangential to the plate at point number 1. Okay, so when it strikes tangential to the plate, there is some angle with respect to direction Fx. That angle also I have shown, that is theta. When it leaves the plate at point number 2, when the jet leaves, the velocity v, that is the jet velocity, is inclined, and its component in x direction is in the negative direction v cos phi. Phi is the angle at the outlet and theta is the angle at inlet. Now look at the expression. Same expression is there, initial expression, that is mass flux multiplied by initial velocity minus final velocity. Mass flux remains same, rho a v. Inside the bracket you can see Vi is v cos theta, because component will have to take in x direction, and minus of v cos phi, because at the outlet component is in negative direction. Therefore the force becomes rho into a into v in bracket v cos theta minus of v cos phi, and finally it becomes rho a v square cos theta plus cos phi. So it is very easy to understand that we'll have to just consider the velocities in the direction of force to be calculated. Okay, let us see one problem. I'll read it. A jet of water 5 cm diameter moving with velocity 25 meter per second strikes normally a smooth plate. Determine the force acting on the plate. Now the plate is fixed. We know the initial equation is case number 1. Fx is equal to rho a v square. Rho 1000 kg per meter cube, that value we know. Area can be calculated as shown and velocity is given. So it is very straightforward, simple problem. Now suppose we'll take another problem where the plate is not fixed but it is hinged. I'll read the question first. A square flat plate weighing 100 Newton is suspended vertically with a hinge at the top. A horizontal jet of water 20 mm diameter impinges, that is impacts, on the plate at center with velocity 10 meter per second. Find the force required to be applied at the lower edge of the plate to keep the plate vertical. The size of the plate is also given. It is 20 centimeter by 20 centimeter. That is 0.2 meter by 0.2 meter. Now here, what we have to consider? As the plate is hinged, it is not completely fixed. What will happen? When the jet strikes the plate is slightly moved. It will rotate at the hinge. Okay. Now, if we want to keep the plate again in vertical position after the impact of jet, we have to apply some force in the opposite direction to the jet, and that is shown here at the bottom of the plate, that is equal to P. The question is, what is the value of P? Okay. Now here, if you see the plate, how many forces are acting on the plate? Force number 1, that is due to the impact of jet in x direction, that is Fx, and second force is the force which opposes the motion or rotation, which is in the negative x direction. So both forces are in x direction only. So the first part we have to rather solve for finding out Fx. Now this is case number 1, that is flat plate. Okay. Now Fx becomes rho a v square, where rho is known, area can be calculated, velocity is given. So we can see Fx is very simple to calculate. But now how to find out P? When the P is applied, the plate should be in vertical direction. Therefore, the P is acting normal to the plate at the bottom, and we have to now apply a moment equation, that is moment of force Fx with respect to hinge and moment of force P with respect to hinge. That two moments should be equal. Then and then only that equilibrium will be achieved and the plate will remain as vertical. Therefore, what I have done, I have written one equation that the force Fx acting at distance 0.1, because the size plate is 0.2 meter by 0.1 meter. So at the center, Fx acts at 0.1 meter from the hinge. So Fx into 0.1 gives you moment from the hinge in anti-clockwise direction. Okay. This should be equal to the moment due to force P, but force P is acting at 0.2 meter from hinge. Therefore, the equation becomes Fx into 0.1 is equal to P into 0.2. Fx is calculated as 1000 into pi by 4.2 square, that is jet area, into 10 square, that is velocity square, multiplied by the distance 0.1 is equal to P into 0.2. Therefore, finally we can calculate the value of